Okay. So I realized the reason I couldn't upload videos longer than 15 minutes is because I wasn't verified on YouTube. But now I'm verified, so I'm like a real YouTuber. Anyways. Okay, we're still talking about series. So right now we're going to talk about absolutely convergent series. So to be absolutely convergent means that you add up the series, but you add up the absolute values of the numbers in the series. So it looks like this. So that is what it looks like. So all of these numbers in the sequence that are getting added up, they're all positive. It's all the absolute value of those. And the reason this is a big deal is because if you think about it, if some of these terms became like negative because of how the sequence is, then it would make sense that it would have an easier time becoming convergent, since it would either get like, you think, like smaller and smaller. But an absolutely convergent series means that no matter if the numbers in the series are positive or negative, it's still going to converge. So that's why it's a big deal. And if it's not absolutely convergent, then it's what we call conditionally convergent. So so far, all of these series that we found the convergence of were conditionally convergent because we didn't test for whether it was absolutely convergent. So conditionally convergent is just your normal series that is convergent. Alright, so now that we have that, let's go over the ratio test. Now the reason I mention the absolutely and conditionally convergence is because ratio tests can help you find absolute convergence. And obviously, if something is absolutely convergent, then it is automatically also conditionally convergent. So, okay. So the ratio test is saying you're going to take the absolute value, because remember, absolutely convergent has to be absolute value of the series. So we're going to take the absolute value and we're going to replace all the n's with n plus 1. I did not need to make this so large. You'll see why I made it so large in a minute. Well, you already know since you've done practice problems. But so if the absolute value of the ratio of the series as n plus 1 over the series as just n equals some number, I'm just going to label it L. If this number is less than 1, then you know the series of whatever it was is absolutely convergent. And if it's absolutely convergent, then you know it is convergent. On the flip side, if this equals, I'll just write it down here. So I'll just put that there. If it's greater than 1, or it equals infinity, then the series is divergent. Infinity, n equals 1. The series is divergent. So you notice how none of these have an equal sign with it? And that's because if it equals 1, then the ratio test is inconclusive. So that's kind of a pity. But yeah. So we can't tell. What this means is that we don't know whether the series is convergent or divergent. I'll just put an arrow there to show that. I'm just like rewriting this here and here. So if the limit is greater than, or if the limit is less than 1, it's absolutely convergent. See? Absolutely convergent. If it's less than 1, it's divergent, and if it's equal to 1, it's inconclusive. So let's do a practice problem with this one. Let's see which one to choose. Okay, I'll do a simpler one to start out. So our sequence is going to be -1 to the n cubed, 3 to the n. Okay. So to solve for the convergence divergence using the ratio test, we want to replace all these n's with n plus 1. So that's just what I'm going to do. So up here, n plus 1, n plus 1 cubed, and 3 to the n plus 1. And then that's going to be over just the, just the regular sequence. Okay, yeah. I'm pretty sure I've been calling this a series, but what's inside the summation is a sequence, because the summation part makes it a series. So this is a series, this is a sequence, but the adding of the sequence makes it a series. Okay, so I'm sorry for that confusion. So now we're just going to write our regular function, and now we're going to solve. So, okay. Remember, the dividing by a fraction is the same as multiplying by its reciprocal. So, the nice part of having this as absolute value is that this negative part, it goes away, because everything's going to be positive. So those essentially just disappear, to be honest. So you can just write n plus 1 third over 3n, and I'm going to split this into 3n times 3. And the reason that works is because one of your exponent properties is that if you multiply exponents with the same base, then it's the same thing as adding those exponents together. So if I have this as a 1, then this is a 1. So this is, I'm going to rewrite it as that. And then the reason I do that is because when I flip this, now this 3n cancel out with this 3n. And I couldn't do that before because this used to be a 3n plus 1, which is not the same as 3n. So now these cancel out. Yeah. And, oh, I undid that. We have the limit and whatever's left over. So n plus 1 to the third, 3n cubed. Now this is nice because if our limit approaches infinity and our degrees are the same, which they both are, this is degree 3, this is degree 3, then we just take the ratio of the coefficients. So there's an imaginary 1 there, and we have a 3 here, so our ratio is 1/3. And as you can see, this 1/3 is less than 1, so that means our series is absolutely convergent. So the way you write this out is you rewrite the series, and you just say is absolutely convergent by ratio test. And that's how you do that. Okay, that one was kind of short, but I'm gonna go eat dinner now, so